Welcome. In this section 11.4, we will be looking or analyzing the domain of the function, the intercepts of the function, the asymptotes, and we'll also analyze the first derivative to see where the function is increasing, decreasing, and giving us the local maximum and minimum. We will be finding the second derivative of the function to see where I have concave upward, downward, and find the inflection points. But before we go ahead, let's go ahead and see what is maximum, minimum, what are inflection points, how can we find the partition numbers. All right, so here I have my function f of c, and as you can see, the function is increasing. Oops, let me reduce this one. The function is, let's try this one more time. The function is increasing, and from that little point there, c, the function starts to decrease. So that c is called local maximum. And as you can see, that is because the function changes from positive to negative. And when is that a local maximum? When f, the first derivative, is 0. Now let's take a look at the next one. The function is decreasing, and then the function starts to increase. And at this point, c, the function changes its sign from negative to positive, and that is my local minimum. And again, we've seen this in the previous section. F prime should be 0 for it to be local maximum or local minimum. Now let's go ahead and take a look here. The function is increasing, and it's still increasing, but f prime is a 0, and there is no change of sign, so that is an inflection point. That is where the graph changes its concavity. This is concave, let me change the color. This is concave downward, and this is concave upward. And again, same thing here. The graph is still decreasing, but this is concave upward and this is concave downward. Now let's go ahead and see some of the most confusing terms here. Partition numbers. So partition number is where f of x is 0 or where f of x is undefined. You can have partition numbers for the first derivative, for second derivative also. Now, critical numbers are numbers where f prime is 0 or where f is undefined. Now, you might say, Miss, what's the difference between both of them? Here, keep in mind for critical numbers, that number, this critical number, could be or is part of the domain. This is usually when the function does not, the function is discontinuous. And here is when the function does not exist. Does not exist. SIST. Oops. Sorry. Let's see. Let's go back to that. What happened? I don't know what happened. No, that's not what I want. Okay. Where was I? Okay, let me erase this one and let's go back. So partition numbers are numbers where the function does not exist. So does not exist. This is where the function is discontinuous. And remember, critical numbers are part of the domain. Partition numbers are not part of the domain. And inflection is where the function changes from concave upward to when the function does not change from concave upward to concave downward. Now let's go ahead and see when can we use these. Partition numbers are used when I'm trying to find the vertical asymptotes, and critical numbers when I'm trying to find the minimum or maximums, and inflection numbers is when I'm trying to find concave upward or concave downward. Now, how do we use them? Partition numbers, you simply set f of x is equal to 0. Keep in mind, for partition numbers, they do not belong in the domain. Critical numbers do belong in the domain. And for critical numbers, I can... Oh, I see what happened. It just got minimized. For critical numbers, I can find critical numbers for f prime. I can also find critical numbers for f double prime. All right. So now let's go ahead and take a look here. If the function is, if f prime is 0 and f double prime is positive, it's concave upward. F prime is 0, f double prime is negative, it's concave downward. But keep in mind, every time the primes are zeros, it's either local maximum or local minimum. All right, now let's go ahead and take a look at the first problem here. What are they asking me to do? They say find the domain and intercept. So let's start with the first one. I will be showing you all different ways to graph this one, but I also want to show you the mathematical way. Again, like always, please read your textbook, the notes, the PowerPoints, and then use this as a resource. That way you'll have a good understanding and you will not be confused or watch these videos again and again just to do that particular problem. All right, so let's go ahead and see how we can find the domain and intercepts. Now you can graph this and find all the information, which I'll be showing you in the end, but also let's take a look at this mathematically. Now looking at the equation, I know this is a rational function. When I have a rational function, I will take the denominator and I'm going to say the denominator cannot be a 0, right? This is a rational function and the denominator cannot be a 0. That means my x should not be equal to 4. So my x should not be equal to 4 because when I have 4 minus 4, the whole thing becomes a 0. Anything over 0 is undefined. So my domain is all real numbers except 4. Now let's go ahead and take a look at the intercepts. Let me erase this one. To find, let's say we are finding the x-intercept. To find the x-intercept, you plug y is equal to 0. Okay, so I'm going to say 0 is equal to 72 over x minus 4. When I cross multiply, I have x minus 4 times 0 gives me 0. 0 is equal to 72. Is that possible? No. That means I have no x-intercept. Let's take a look. I have no x-intercept, or there is no x-intercept. Now let's go ahead and take a look at the y-intercept. To find the y-intercept, I plug x as 0. So I have f of x is equal to 72, 0 minus 4. So I have 72 over negative 4, and that would give us negative 18. So my y-intercept is negative 18. Now let's see what we have. Yeah, that's all we need to find for this one. Now let's go ahead and take a look at the next problem. What I'm going to do is I'm going to delete this one so we can see and graph it from the beginning. Use the information to sketch the graph, okay? They said domain is all real numbers. Very good. So it's a continuous function. And I have limit x goes to infinity. I have the function value going to 3. Keep in mind, again, this is a good segue to remind you all to review your horizontal asymptotes and your vertical asymptotes. Very, very important, especially during when you're graphing the rational function. So please review your horizontal and your vertical asymptotes. Again, horizontal asymptote, something like this, right? Oops, different pen. Horizontal asymptote is horizontal, vertical asymptotes is vertical. Remember, the graph doesn't touch. The graph either goes to negative infinity or the graph goes to positive infinity when you are looking at the vertical asymptote. So let's go ahead and take a look here and see what this is. So the first step is, I know that when x goes to infinity, the function goes to 3. So what I'm going to do is I am going to expand this one, and I'm going to make sure I graph the graph, and I'm going to plot these points, negative 4 and 0, okay? So negative 4, let me have negative 4 here, negative 2 here, 0. Again, this is not to the scale, so this is positive 2, this is positive 4. I'm plotting these points. Negative 4 is a 0. Negative 2 is negative 2, so somewhere here this is negative 2, let's say. Negative 2 is negative 2. 0 is 0, 2 is -2, and 4 is a 0. These are the points in my graph. Now, because these are points in my graph, I know my graph has to pass through this point and go all the way up to 0, pass through 0, pass through this point, and pass through this point. Now the question is, what is going to happen to my graph after -4? So let me change the color again. Will the graph go like this, or will the graph go like this? Will the graph go like this, or it's going to be like this? That's where the question comes in. So let me erase these. And let's go back to the function. Here they told me that when x goes to negative or positive infinity, my function goes to 3. So let me draw a line at 3. This is going to be my horizontal asymptote. And now, even without any further information, I know when x goes to infinity, my graph would go close to the horizontal asymptote. Right? Now let's go ahead and see if that is right. I'm going to use this information and I'm going to graph here. F prime is negative. That means the graph is decreasing and it's 0. So that means there is a local maximum or minimum here. And F prime is positive. That means the graph is increasing. Again, this is a 0. That means there's a local maximum or minimum. The graph is decreasing and then the graph is increasing. So my graph should be like this. Okay? And now let's take a look at F double prime. F double prime, it's negative. So this is concave downward, concave upward, and then concave downward. And let's see if that is happening here. So up to -2, the graph decreases. Up to -2. So this is decreasing, decreasing, decreasing up to -2. That's good. And from -2, the graph is increasing, and then the graph is decreasing, and then the graph is increasing. So this part is done. Now let's take a look at concave upward and downward. Up to -4, the graph is concave downward. Do you see that? The graph is concave. Let me use a different pen. The graph is concave downward up to -4. From -4, the graph is concave upward up to +4. Concave upward, concave upward, concave upward, concave upward. And from -4, the graph is again concave downward. And now let's go ahead and reveal the final answer. There you go. All right. Now let's take a look at the next question. And again, please keep in mind, if you're having any questions, pause, rewind, and you can even run this video at a slower pace or faster pace. So make sure you do that as well. Now let's go ahead and take a look. Again, I want to go ahead and take this off so we are not looking at the graphs. And now let's go ahead and graph this. I'm going to draw my X and Y axis. So domain is all real numbers except -6 and +6. So that means I know I either have a vertical, I have vertical asymptotes, or the function is discontinuous at that point. And I have f of -9 is -4. So I'm going to go ahead and graph that. -9. Again, this is not to scale, remember. -9 is -4. I'm going to use a red dot here. Very good. I have +9 is +4. Again, +9 is somewhere here. In +9, +4 is somewhere here. I'm going to use a red dot. +9 is +4. And I have f prime. So I'm going to come back to this one in a minute. I have f of first derivative and I have second derivative, but the information they gave me is I have a vertical asymptote at -6 and +6, and I have a horizontal asymptote at y is equal to 0. So I am going to graph my vertical asymptotes at -6. So this is my -6, and this is my positive 6. And I have my horizontal asymptote at 0. So this is my horizontal asymptote. Actually, let me increase the line so y'all can see. Horizontal asymptote. Okay. Now that part is done. And now, because this is a vertical asymptote, this is a horizontal asymptote, I know my graph has to go through this way because it has to touch the point. There's no way the graph is going to go, let me erase this one. There's no way the graph is going to touch this point and go back up like that. That's not possible because of the only reason that these are my asymptotes. And on this side, I know my graph is going to touch this and okay. So what I'm going to do is I'm going to bring these down just a little bit so we can see. And I'm going to move my point 4 also all the way down. There you go. And now let's go ahead and see. F of 0 is 0. I did not plot this point. F of 0 is 0. So f of 0 is 0, this point. So you know the graph has to pass this line. Now the question is the graph going to be like this? Is the graph going to be like this? Or is the graph going to be like this? Or is the graph going to be like this? Now you might say, Miss, why are you using those lines? Because these are asymptotes, remember? The graph cannot pass these lines, okay? So now let's go ahead and see how the first derivative and the second derivative are going to help us. According to the first derivative, f prime is less than 0. That means it's decreasing from negative infinity to negative 6 and 6 to infinity. F prime is greater than 0. That means it's increasing from negative 6 to positive 6. Okay? So from negative infinity to negative 6. I should probably have this. This is negative 6. This is positive 6. So let's see. The graph is decreasing. Yes, the graph is decreasing. And from 6 to infinity, the graph is decreasing as well. Now, in between negative 6 and positive 6, the graph is increasing. That means my graph is going from lower end to upper end. It's going up. My graph is increasing. Excuse me. Now let's go ahead and take a look at the second derivative. What does second derivative tell me? It says that it is negative. That means concave downward from negative 6 to positive 6. Yes, it is concave downward. And it is concave downward from negative 6 to 0. So in this area, also, this is concave downward. And it is greater than 0 from 0 to 6. This is concave upward. This area is all concave upward area. And this was concave downward. And it tells me that it is concave upward from 6 to infinity. Yes, I can see the graph is concave upward. It's concave upward is it's up and concave downward is down, right? That's what I have. Now they're telling me that the graph is concave downward. That means my graph is going to be concave downward this way because it has to touch this point. Remember, it has to touch this point. And then from here, my graph is concave upward. And yes, when I look at my first derivative, the graph is increasing. I'm not going down here. I'm only going, what color can I use? I'm only going up. My graph is only increasing. Okay, so just based on your first derivative, second derivatives, you can see how the graph goes. Because my only options were this, and let me change the color. My other option was my graph going something like this. This is one graph, or my graph going down, or my graph going from this side to this side. But none of that is, I mean, that could be possible, but I know I have to match my first derivatives and second derivatives. It said my graph is increasing throughout. Yes, my graph is increasing. It said my graph is concave downward. Yes, my graph is concave downward from negative 6 to 0, and then it becomes concave upward from 0 to positive 6. All right, let's take a look at the next one here. It said summarize, and it gave me the function log x. In this case, I'm finding the domain, my x-intercepts, my y-intercept, my vertical asymptotes, my horizontal asymptotes, whether my function is increasing or decreasing, concave upward, concave downward, and inflection points. Now you can start with graphing this and then working it out, but I would like to go ahead and do everything step by step. All right, so let's go ahead and start with the domain. This is my log ln function. Let me use black color here. This is ln x squared plus 64. And keep in mind, log functions have to be greater than or equal to 0. So this x squared plus 64, and I'm trying to see where this is greater than 0. This is positive. This is positive. So this is the domain of this ln function is all real numbers. And as you can see, the domain is all real numbers, because there's no way this function is going to be discontinuous. This is a positive function. Both of them are x squared and x squared, and this is always going to be x squared. Or you can just simply say x squared plus 64 is greater than or equal to 0, and x squared is greater than negative 64. And I know I cannot have any imaginary numbers, so that means the domain is all real numbers. And again, you can start with graphing it and then looking at the domain. Now let's see what the x-intercepts are. So ln x squared plus 64. How do I find the x-intercept? I'm plugging my y is equal to 0. So ln x squared plus 64 equal to 0. This is the log function. So I'm going to change this into exponential. So x squared plus 64 is e to the power 0. X squared plus 64 is 1. X squared is equal to negative 63. X squared is, x is square root of negative 63. Those are imaginary numbers, so I don't have any x-intercept. So very important. Like I said, start with the graph, which I'm going to show you in a minute, but I want to do everything mathematically first. So we have no x-intercepts. And now let's go ahead and take a look. No x-intercept. Now let me go ahead and find the y-intercept. How do I find the y-intercept? I plug my x as 0. So ln 0 plus 64. So I'm looking at ln 64 is my y-intercept. Remember, you plug your x as 0 for your y-intercept. So when you plug ln 64, that will give you 4.2. And now I am looking at my vertical asymptotes. This is not a rational function. This is not a, oops, my eraser is not working. This is not a rational function because I don't have any denominator. So I don't have vertical asymptotes. So no vertical asymptotes. And again, I don't have any horizontal asymptotes as well. Asymptotes. All right, let's go ahead and take a look. Oh, it's right here. There are no vertical asymptotes. There are no horizontal. This is not a rational function, so there's no vertical asymptotes and no horizontal asymptotes. Now, this is where the challenge comes in. I am looking at the first derivative. Now, let's go ahead and jump deeper and see where the function is increasing, function is decreasing, concave upward, concave downward, inflection points, partition points, right? Inflection points and partition numbers. The first thing I'm going to do is find the first derivative. This is ln, so 1 over x squared plus 64 times derivative of x squared is 2x. And my first derivative is 2x x squared plus 64. Now let's go ahead and find the second derivative. I'm going to use a different color. F double prime of x is, the derivative is going to be x squared plus 64 whole squared times x squared plus 64, derivative of 2x is 2, minus derivative of x squared plus 64 is 2x times 2x. Now when I simplify this further, I have 2x squared plus 64 is 128 minus 4x squared over x squared plus 64 whole squared. Let me simplify this further. I get negative 2x squared plus 128 over x squared plus 64 whole squared. Now if I take out x squared, now if I take out a 2 from here, I will have negative x squared plus 64 over x squared plus 64 whole squared. Now that I have my first derivative and second derivative, let me erase, oops. Now that I have my first and second derivative, what do? Remember, the first derivative gives me where the function is increasing or decreasing. So I have to find my partition numbers. And here, I'm going to set this equal to 0 plus 64 equal to 0. That means my 2x is equal to 0. That means my x is equal to 0. So my partition numbers are, on my number line, I have a 0. So now you will see what's going to happen from negative infinity to 0 and from 0 to infinity. So you're trying to see what's happening to the function in this region and in this region. How would you do that? All you have to do is take a value. I'm going to take negative 1 and I'm going to take positive 1 to keep my life simple, and I'm going to go ahead and plug into the function. So it's 2 times negative 1. I don't have to plug in the denominator because everything is going to be positive, because everything is square. Remember, I'm not trying to find the value. I'm only trying to find, is it positive or negative? So this is always going to be positive. So when I plug negative 1, I know that this is going to be negative. And when I plug positive 1, I know this is going to be positive. So what do I know? I know that my function is increasing from negative, no, sorry, my function is decreasing. It's negative, right? My function is decreasing from negative infinity to 0, and my function is increasing from 0 to infinity. That's what the first derivative gives. Let's go ahead and take a look. As you can see, my function is increasing from 0 to infinity and decreasing from negative infinity to 0. Now let's go ahead and look at, where is the function concave upward or where is the function concave downward? All right. To do that, I will take my second derivative, and what do? Set that equal to 0. So remember, the first derivative gives you whether the function is increasing or decreasing. The second derivative is going to give you concave upward and concave downward. Again, please hold. I will show you all of this using the graphs, but it's very important to know the math. So I'm going to cross multiply. When I cross multiply, I will only have 2 negative x squared plus 64 equal to 0. Or in other words, negative x squared plus 64 is equal to 0. I divide by 2 on both sides. And I have, if I bring negative 64 to the other side, I have x squared is equal to 64. So I take x squared to the other side just to make it positive. When I take x squared to the other side, I have x squared is equal to 64, x is equal to positive or negative 8. So here, my partition numbers are negative 8 and positive 8. So what you're trying to do is you're trying to see how is your graph up to negative 8, how is your graph from negative 8 to positive 8, how is your graph from positive 8 to infinity. And again, do not forget to put negative infinity and positive infinity here. What do? Simply take a value and plug it into the function. And again, I'm not trying to give the exact number. My goal is to see, is it positive or is it negative? That's all I care. So what I'm going to do here is I'm going to take a number. I'm going to use my red color. I'm going to take a 0 here because that's easy. And I'm going to take number 9 here. And I'm going to use the same number with a negative sign. And again, keep in mind, my goal is to see if this is positive or negative. So all I'm going to do is take negative 9, take a 0, take the 9, and plug it into f double prime or second derivative. Same concept. I'm going to rewrite this one here. I have 2 negative x squared plus 64 over x squared plus 64. I think it's whole squared. Yeah, whole squared. Again, I don't have to plug in to this one because this is always going to be positive. I only plug in the top to see what my numbers are. Okay, to do that, I will take negative 9. So 2 minus negative 9 squared plus 64. You can use your calculator to do that. And when I look at it, negative 9 squared is 81. 81 minus 81 positive 64. I'm going to get a negative here. Now I'm going to go ahead and take, again, you can plug this into your calculators to see if you get a positive or negative. And now I'm going to take a 0. When I plug in 0 here, I have 2 times 0 squared plus 64. I know it is going to be a positive. Now if I take positive 9, 2 times negative 9 squared plus 64. Remember, I'm not doing the denominator because I know it's always going to be positive. So negative 9 squared is 81, negative 9 squared is negative 81 plus 64. I know I'm going to get a negative. What will I know from here? From here, I will know that if my graph is concave upward or concave downward. This is negative, that means my graph is concave downward. This is positive, that means my graph is concave upward. This is negative, that means my graph is concave downward. So from negative infinity to negative 8, and from 8 to infinity, my graph is concave downward. And from negative 8 to positive 8, my graph is concave upward. So let's go back here and see if we have that. My graph is concave upward from negative 8 to positive 8 and negative infinity to negative 8 and 8 to infinity. And as you can see, my inflection points are negative 8, positive 8. Right? That's where my inflection points are because this is 0, this is 0. It is changing from negative to positive, inflection point, positive to negative, inflection point. Now that we know all of this, how do we graph it? Let's go. I luckily don't have an x-intercept, but I've seen that I have a y-intercept of 4.2. So I'm going to say this is my y-intercept of 4.2. And my graph is decreasing. These are my inflection points. Negative 8, positive 8. Oops, my stomach's growling. Excuse me for that. What were my inflection points? My inflection points were negative 8, positive 8. Yes. Okay. So I know my graph was decreasing and then it increases. Let me minimize this whole thing here so it's easy for me to graph. I'm just going to put negative 8 here. I'm going to put positive 8 here. My y-intercept is 4.2, so I know I have to touch this point here. And I know my graph is decreasing. It's concave downward up to negative 8, and then it's concave upward, and then concave downward, and then, no, concave downward, concave, I can't even reach this point, concave downward, and then concave upward. Oh, come on. I'm trying to get it to this point here. Concave downward, concave upward, and concave upward. Where else is my graph? Concave upward. My graph was concave upward, all of this, and then concave downward. So you get the idea. So when I look, no, I don't have so many inflections. Yeah, I do. So when I look at the graph, you see it's concave downward, and then concave upward, concave downward, and then concave upward. So that's how, it's not exactly the same, but these inflection points are really small. So it's going to be, sorry about the sound, inflection points, right? Now, you might say, Miss, can I use my Desmos or can I use my graphing calculators? Of course, you can use Desmos in the test because of MyMathLab, but you can use your graphing calculators. So let's go ahead and graph this one. And I have ln x squared plus 64, it was, yeah. So you see in the graph, you just see a graph going up and down, but there's no way you can find the inflection points, -8 and +8. But there's a slight dent in the graph here. If you look at it, it goes concave downward, and from -8, it starts to become concave upward, and then, so, but to find those -8 and +8, you have to do it mathematically, but you can start from this graph here. As you can see, there is no x-intercept. My y-intercept is 4.2. My graph is decreasing all the way up to 0, and then my graph is increasing from 0, and at this point here at +8, there was concave downward. So all these points are very important, and you can get those numbers only from your graph. So this slight dent is very, very minimal. You will not be able to see that in your graph as well, but you have to get these numbers only by calculating the second derivative. All right, again, concave downward, concave upward, and all these numbers, you will only get them from just by calculating your first and second derivative. Now, there will be cases where you can just get all your information from the graph. Like in this one, what I'm going to do is I'm going to go ahead and have this app right here, maybe to the right. Let me put this to the right. I'm just going to slide this over. Okay, never mind, it's not sliding. I'm going to go ahead and graph this one. Going to move this side. I'm going to graph. The graph is x squared divided by x minus 7. And here, I'm trying to see what my domain is. And as you can see, when I expand this graph, can I expand this? Yeah. When I expand this graph, this number is 7. This number is 7. Your asymptote is 7. And again, you don't have to do that. Just by looking at the denominator, you know that your asymptote is 7. Your vertical asymptote is 7. So x minus 7 should not be equal to 0. So your domain is all real numbers except 7. And that's exactly what you have here. And looking at the graph, you do have an x-intercept, which is 0. And that's what you have here, 0. Y-intercept, the graph passes through the origin. So your y-intercept is also 0. Now let's move to the next one here. There are no horizontal asymptotes. Again, just by looking at the graph, you can see that there are no horizontal asymptotes. And if they ask for the vertical asymptote, again, clearly, x is equal to 7 is your vertical asymptote. Let me go ahead and graph x is equal to 7. There you see, that's your vertical asymptote. And also from the denominator, you know that your vertical asymptote is x is equal to 7. And let's look at the next part here. Now they're asking me, where is the graph concave upward or concave downward? Looking at the graph, concave upward is from 7 to infinity. So 7, this whole thing up here, can I point this? Yeah, this, no, this graph. Okay, let me, the whole thing up here is concave upward. So from 7 to infinity, your graph is concave upward. And from negative infinity to 7, your graph is concave downward. Just by looking at the graph here, you can point that out. And as you can see, there are no inflection points. There's no change from concave upward to concave downward. This whole thing is concave downward, and this whole thing is concave upward. There is no shift from concave upward to concave downward, or from concave something like this. There's no shift. We don't have any inflection points. It's continuously concave downward, or it is concave upward. So even from the graph, you can pull out your information. But again, it's very, let me close this one. But it's very important, you know, that you're finding your first derivative. Where is it? You're finding your first derivative to see where your graph is increasing or decreasing, and your second derivative to see where your graph is concave upward or concave downward. And the point where the graph changes from concave downward to concave upward, or from concave upward to concave downward, or your inflection points, like here, concave upward, and then it goes concave. Here, let me use a different color. Concave upward, and then the direction goes concave downward, and then concave. It's all concave downward here, and then concave upward. All right. Hope this helps.